Good morning, thanks for coming. I'm happy to see many people again in one of our colloquia. Today we discuss gravitational waves. You've all seen the announcements of the discoveries by LIGO and Virgo. Today I'd like to find out what we can learn after digesting these first signals for a year or so. What particle physics can we extract? I think that's an interesting question, and I hope our speaker can give us an answer. He is Jo van der Brand of NICEF in the Netherlands. He's the spokesman of the Virgo collaboration and one of the key players in the European Gravitational Waves community. That community is organizing itself already for the next generation of projects, so I hope he can also introduce us to LISA and the Einstein telescope, which would be the future of gravitational wave detection. Thanks for coming, Jo, and go ahead.
Thanks for the invitation and the nice introduction. So I'm a professor at the University in Amsterdam, and that is a member of NICEF. NICEF is the National Institute for Subatomic Physics in the Netherlands. It's an organization of 5 universities. And before I was doing gravitational waves, so about 10 years ago, I was working on LHCb at CERN and CP Foundation B Physics. And actually I was the project leader of the vertex detector of LHCb. At that time it also sounded like an impossible experiment to me. So then we decided to go into gravitational wave science, and at an institute like NICEF, which is purely particle physics, you can imagine what kind of discussions we had before finally everybody agreed that we started doing this science. So isn't this astronomy? What has it to do with fundamental science and things like that? So the talk that you will hear today is purely from the viewpoint of somebody coming from particle physics. So my apologies to many friends in astrophysics and in astronomy, but I will more emphasize the other topics. So why gravity? Gravity is a fundamental interaction, and actually a very important one, and also the one where maybe the biggest questions in science right now are in gravity. So it's the fundamental principle of organizing structure in the universe. And then if you take the best theory that we have of gravity and you compare it to all the information that we collected about the universe, and you try to describe what you see, then it just doesn't fit. And it doesn't fit a little bit. There are quite sizable deviations. So everybody knows about the story on dark matter, and you need about 5 times more matter than what we see in order to get agreement in our descriptions. Gravity, normally you would think of something that is always attractive, but we see an accelerated expansion of the universe. So we have these terms like dark matter, dark energy, but maybe this is signaling something else. I think right now is the right time to scrutinize the gravity. Many people are working on that, so there is a tremendous worldwide intellectual activity on this topic, and both, of course, from the side of theory, it's all trying to get a unified view on that, but also from the experimental side. And more data sets will become available in the CMB, but also with LSST, etc. in future. So what we are trying to do is get a view on this from the experimental side. So now if you look at gravity, and you ask yourself, so what is the dynamical part? So the dynamical part, that are the gravitational waves. And so that is what we are trying to study. It is difficult to do that. The interaction is weak. It's very difficult to detect them. You also can put this in a positive way and say, it's an ideal information carrier, because once it's created, it almost practically doesn't attenuate, and it goes. The universe is transparent for gravitational waves. Might actually be the only way to look back all the way to the Big Bang. And the universe is transparent down to 10⁻44 seconds after the Big Bang for gravitational waves. The only question is, what will we see? And I think that is not known at this moment. So I think it can have quite some impact, and what I will do is I will talk about the fundamental physics with gravitational waves, and then maybe what new insight we could get on cosmology with this. So it all started with Einstein, who thought very deeply about what is space and what is time. You could say, these are simple questions. Space is where something happens, and time is when it happens. But it's a bit more complicated than that. He found out how gravity fit into that, into the curvature of space-time. And many more things came out of that theory, like the expansion of the universe, other solutions, like black holes, or more like that, more things even than that. And in that theory, so the gravitational waves are perturbations in space-time and that travel through space with the speed of light in that theory. Actually, when he had in November 1915 a general relativity, already the next year he came with the publication on gravitational waves. And if you read that publication, it's interesting. There are two things at least that appeal to me when I read it. And one is the constant that he calculates there, and he comes to the conclusion that the effect is small, so small that probably will be insignificant for any practical purposes. So he doesn't believe that practically you could see something like that. So that is the constant A. The other thing that I found interesting in that paper is that he compares it to electrons moving around in an atom, and then they cannot radiate. So you need quantum effects in order to forbid the radiation that you would have in Maxwell's theory. And he says something similar probably will happen with gravitational waves. And that is, as far as I know, the first mention of quantum gravity that I saw in any paper. So it took indeed quite a while to build detectors that are sensitive enough, and that was already going on. The first ideas came in early 60s to use interferometers to do that. Then it was Ray Wise at MIT that realized that if you do it that way, then you need kilometer scale interferometers. And then it took a while to get funding for these projects. So that started in the 1980s. And already around 2009, 2010, the detectors, the LIGO, Virgo, and Geo600 detectors were running. We spent more than a year taking data, but we didn't see anything. And so then we decided to upgrade all these instruments. So all four of them were upgraded, and that is called the second generation. So these are the advanced LIGO and advanced Virgo detectors. So the idea is that you make them 10 times more sensitive. If you make them 10 times more sensitive, you look 10 times further into the universe, and the volume of sources goes with the third power, so your event rate should go up by a factor of 1,000. Now we had 0 event rate, so was a risk that it again would be 0. Actually, we didn't reach the factor of 10 yet. So far, when LIGO came online, we reached about a factor of 3. But even that factor was enough then to get the first detection. It was interesting that it already happened in the first week, but okay, I don't know why this occurs. Here you see one of the detectors. This is the one in Hanford, so the state of Washington. So these are tubes 4 kilometers long, huge vacuum system. This is in Louisiana, so in a swamp. And so these are large-scale interferometers. A bit more complicated than a normal interferometer. And if you have time, I will say a bit more about it. So we turned them on, and actually we were supposed to start at the end of the week on a Friday in the second week of September. But if you would have been there, this is what you would have seen. 2 black holes of about 30 solar masses each colliding and to form a black hole in 62 solar masses. So the green stuff that you see there is supposed to be a gravitational wave. Of course, everything is space-time. So the background is space-time, the black holes are space-time, gravitational waves are space-time. So it's interesting. So these waves then go through the universe. More than 1 billion years. They have been traveling and then losing their amplitude with 1 over the distance. And then the 14th of September they hit Earth. came in a bit from the south, and yeah, this is what happened then. Maybe larger scale, but this is what occurred. It was seen by these two detectors. These were the detectors that were on. Also the detector in Germany was on, but that is only sensitive to higher frequencies. And the surprising thing here is that the frequencies were low. I, at least at that point, expected that the first event would probably be the collision of two neutron stars. And so we know what to expect for a signal. But the signal that we saw is the signal that you see over here. That lasted only 0.2 seconds. That was already very strange. And the other thing is that the amplitude was huge. So half of my group is in data analysis and trying to filter out the signals from the background. So actually you don't need that. You see by eye. So we still didn't fire the group. But so when you take the so on the left top you see the signal a little bit filtered in the handphone detector. Then on the right top you see the signal in Louisiana. That the detector is oriented in a different way, so you multiply by a minus sign and you shift by 7 milliseconds on top. Then you can compare it to solutions from numerical relativity. And if you subtract, then if the signal is described well by the theory, then what you should see is something that is consistent with noise. Now the problem with our noise is that it's non-Gaussian and it's non-stationary. So it's quite an effort to really do the statistical analysis. And this is what you see in these time frequency diagrams. So you see a chirp, an increase in amplitude, and at the same time an increase in frequency. Very characteristic of two objects rotating and then merging together. So by just looking at this plot, you immediately can draw some conclusions. If it would have been the neutron stars that would have merged that I expected, then you can do calculations, and the highest frequency that you would see goes up to 1.6 kilohertz. But over here, it goes up only to something like 200 hertz. And so clearly it was a much heavier system than two neutron stars. Why do I talk about two neutron stars? Because we have seen these systems. We know that they are there in the sky. We know that they are losing energy and that they will merge. So we can do calculations on them, and we know what to expect. We didn't expect these black holes. That was at least to me a tremendous surprise to see them and to see them so heavy. What we can get from the analysis quite precisely is a combination of the masses of the objects. It's called the chirp mass. And the maximum frequency of the inspiral phase, and where it's going around each other, it's proportional to 1 over the total mass. But the total mass and the individual masses are much more difficult to get at. Then in general relativity, the phase evolution is very well described, actually up to 7th order in V over C. And so we can test general relativity and see how it compares to what we measure. You also see that if you do a simple calculation, what is the speed with which these objects are colliding, it's more than 50% of the speed of light. And another thing that is important is that the strain, if you look at the signal, and you know the frequency behavior, you actually can calculate the luminosity of the source. So by comparing what you measure, you know the distance. So this is a way to get at the source distance in a completely independent manner. Now you've seen all of that before, and you know that we have published so far 6 of these events. 5 of them are at the level of more than 5 sigma significance. So that means that the chance that this is noise that is making this is less than 7 parts in a million. There was only one event which we call a LIGO Virgo trigger, which is not that significant. It's not even 3 sigma. You see the chirp, the correlation in the masses is well known, but the individual masses is actually not so well known. Then what we can do is can get at the masses, we can try to get at the spins, at the distance, at the inclination, and things like that. So the first thing that we did is now compare what we see to theory and do a test of general relativity. So the test that we do is what we see in agreement with general relativity or not. We don't have a preference for any other alternative theory, only do that test. And then what I told you is that the phase of the spiral is very well known, and you can compare what you see to the phase that you measure. And you see, for example, if you look at the 1.5 pm post-Newtonian term, then combining three events, we do a Bayesian analysis, so we can combine information from different events. You already see that we tested this at the 10% level. So that 1.5 pm term has physics in it, and the physics has to do that, I told you, everything is space-time in these events, and the gravitational waves can scatter from the curved background space-time. And is that scattering, the back reaction, described in a correct way? And at least at the 10% level, it seems that this is the case. This you could not have tested in any other way. So this is the first time that we know this. The other things, if you go to higher terms, then you can test, for example, how is the coupling, the description between the coupling between the spins and the orbit, and things like that. So that is what we're trying to test. So this is only with a few events. Hopefully, if we improve our sensitivity, we will end up with hundreds of these events, and we will go to test this at a more precise level. Then you have the merger phase and the ring down phase, and I will tell you some more about that. So the bottom line is that there is physics in all of these tests. Of course, you can ask yourself the question, given that everything that seem to be solutions of general relativity, and also the problems that people see with black holes and trying to combine it with quantum mechanics, for example, the information paradox and things like that. People are inventing, theorists are inventing all kinds of alternatives to classical black holes in general relativity. So you can ask the question, so what you have seen merging there, how certain are you that these are really black holes and not something else, not another solution? Now, we are not completely certain, but the best evidence is this for that first event. So if you take any substance, for example, you take a piece of wood or a piece of metal or glass, and you want to learn about the substance, you can excite it, you hit it with a hammer, and it will ring at certain frequencies, and the frequencies, they will ring down, and they will have exponential decay. If you do this with a black hole, then at the end, that black hole that is formed is a curve metric, but before the formation, it came from two colliding black holes. So it's like an excited state that is ringing down to its curve metric. You can calculate in general relativity what the frequency is of the dominant mode, and that is indicated by this black circle here. And it should be about 250 Hertz, and it should decay with about 4 milliseconds. And we can compare that to what we measure, because you see on the right the ring down frequency and the decay time. Of course, you have to wait a bit until you're certain that the complete horizon has formed. It takes about 3 milliseconds. And then, indeed, this is what you observe here in purple. And so this is right now the best evidence that we have that indeed this is consistent with a black hole. This is absolutely not watertight, foolproof evidence. What you need to do it correctly is measure also the higher order modes, and that the ring down times also of the higher order modes. We will do that. We need higher SNR, signal over noise, on our events. So we need to improve our detectors more and more. So we will do that. So this is one of the things that we will do. And then by doing that, you can also form more rigorous tests of general relativity, like no-air theory and things like that. Another thing is that gravity is in a quantum theory or not? I have no opinion on that. I'm an experimentalist. I try to do the measurement and then compare to what people predict. But if it is a quantum theory, then there is a quantum particle, which we call the graviton. So I don't know whether it exists, but if it exists, it will affect the phasing of the gravitational waves. So it's a simple calculation to do that. And and it actually ends up the phase of the 1.5 pm component, which we can measure precisely. And if there is a little dephasing in one of these pm components, and this is accumulating over 1 billion years, over 2 billion years, then we can put a limit on that. So the limit on the Compton wavelength right now, from this first event is already larger than this. And on the mass of the graviton is that we know it's, if it exists, it's smaller than 10 to the minus 22 electron volt. So to put this in context, we also know that we have quantum electrodynamics, where we have a photon, when we say it's massless. But this limit already is 10,000 times more stringent than the limit on the mass of a photon from one event, lasting only 0.2 seconds. So that is what we know. You can do more than that, because there is nothing that prevents you to write down a generic dispersion relation, the relation between energy, momentum, and generally then it's the mass of the particle, but generalize that. And now, if you have a deviation from that dispersion relation, also that you will see a dephasing of the different wave components. And we use that, again, to put limits on deviations from Lorentz invariance. Also, that is a published result. If you do that, because several modified theories of gravity are predicting values for that, for this alpha. And right now, we can exclude some of these theories, for example, having to do with extra dimensions or other things. You can do more than that. And these mimickers of classical black holes, they can come in all kind of forms. So you can have the quantum modifications that I talked about. People talk about boson stars, fermionic dark matter, graviton stars, where you have mass colliding into a black hole with some kind of repulsive space-time, making some equilibrium there. All with the idea that you keep the mass outside the horizon and you don't violate the information paradox. So if you would have things like that, you would get echoes. And these echoes, for example, in the case of wormholes or graviton stars, we can look in the data. People are doing this kind of analysis and putting limits on the existence of that. There are claims in our collaboration, LIGO, Virgo, we don't support this for the moment. So these were a few examples. So all the results on the first collisions of black holes were obtained with the two LIGO detectors. It took a while to get the Virgo detector, the European detector, operational. And actually, the LIGO, the second observation run was started with the two LIGO detectors in November 2016. And it would end on the 25th of August in 2017. And only by the 1st of August 2017, we were ready to join. At the moment when we joined, I knew about two events, one in January and one in June. So my expectations for the 3.5 weeks of joining were not very high. Okay. So there was no reason to have these expectations. So this was a tremendous amount of work. I got elected spokesperson in May. At that point we had a range of BNS of 0.13 megaparsec, which is, so it took until the middle of July to improve that by a factor of 200, and then we could join. Before we joined, we had to do an engineering run to demonstrate stability of the device, and then on the 1st of August we joined. University of Valencia is, of course, a partner in all of this. There are 6 countries involved. I will skip the instrumentation of this. If you have any questions on instrumentation, ask me, but I'll prefer not to do that. The science run was actually quite reasonable for Virgo. We were stable, so our sensitivity might not be the best sensitivity, but the device was very stable. So that tells you that inherently the quality of the optics and all the components is very high. Otherwise you cannot reach its stability. But you have to tune it to the right setting. And we didn't have time enough, so the best that we could do was something like 28 megaparsec. And right now we are above 31, that is what we achieved. We want to run again this year in the fall, and we are aiming at least 60 megaparsec to achieve that, which is not easy. And we had very high efficiency, 85% data taking efficiency. So that was quite good. So we got now also triple coincidences between the two LIGO detectors in Virgo, and additional advantages that I will tell you a bit about it. So when we turned it on, already within 2 weeks we had our first detection. This came on the 14th of August. And you see our sensitivity is lower than the two LIGO detectors, but still after analysis it's 4.8 sigma significance in the Virgo detector. And this is two black holes colliding, 31 and 25 solar masses. And then it looks a bit like the first event. And I don't know why they immediately happen when you turn the device on. It's fine with me. So this was very positive, we were happy. And also if you have a detection with 3 detectors, you can do sky localization much better. And so up to, with only the LIGO detectors, typically you have about 1,000 square degrees on the sky. It depends a bit where the source is, can be 1,500 square degrees. But in this event it was 60 square degrees. So for astronomers, you shouldn't laugh. I know it's still very large, but this, for a gravitational wave science, this is actually quite good. We improved it by a factor of 20. With 3 detectors, we also can measure the polarization of the source. Actually, with 2 non-aligned detectors, you can do that. And in general relativity, this is this H plus and this H cross. And you can do 2 things at least with that. One is that if you look at the binary system, if you look edge on in that system, you only have plus polarization is what you measure. While if you look so face on a device, on a binary system, you get circular polarization, an equal mix of plus and cross polarization. So by measuring the polarizations, also with Virgo, you can get a handle on the inclination. Now how good that is depends a bit on your sensitivity and where in the phase space the measurement is done. So this was the first measurement of that. Another thing that you could do, but it's more an exercise than anything else, is that you can assume that you have a theory with only scalar polarization, only vector polarization, or only tensor polarization. Then in general relativity, you have 2 tensor polarizations, but in general metric theories, you have 6 possibilities. And then we do the analysis for only pure scalar vector tensor, and we see what the data prefer. And the data prefer pure tensor. So in that sense, it was another check of general relativity. So this detection was made on the 14th of August, and this is when we announced the result. This was the 27th of September. So this was one of the fastest analyses that I ever did in my life. So we did the analysis. We were scrutinized because this was the first detection by Virgo. So that means that we have to go through the entire Virgo enterprise to see that everything is working correctly, that the calibrations were done correctly, that it was not noise. Then the paper had to be written, the whole collaborations had to be behind the contents of the paper. Then it had to be submitted and reviewed. And it was accepted by Fiscal Letters a few days before the 27th. So then we announced it in Torino at the G7 science meeting. We were in a hurry because we knew that we had detected more than this. And we wanted to get this event out and show that we could do the detections with gravitational waves. So this was the 27th of September. The 3rd of October, so that the week after the Nobel Prize was awarded to the people over here. And it's nice that Virgo was mentioned in that announcement. So this was good news. Actually, I went to your science museum yesterday, and they have on the 2nd floor a hall on the Nobel Prizes. And when I came there, I looked at the board and the prize of 2016 was on. But the woman was just coming in with the posters for the 2017 Nobel Prize. So right now they should be in the Science Museum, also here in Valencia. She was surprised that I was making a picture of her. So we had the first detection in Virgo on the 14th of August. And 3 days later, we had another detection, the event, the binary neutron star. And so this was extremely exciting. It's one of these things that happen that you know exactly where you were. I was in that office, and Chris van den Broek, who was doing data analysis, was running, shouting in the corridor that we have detected the gravitational wave. And we immediately went into live connections with LIGO to make sure that we could announce this to the world, that we could make our sky localization map, and that we could give this to astronomers. And we intend to do this automatically for the next run, starting at the end of the year. It took us 5 hours to get the sky map out, which is really a bit embarrassing, but we couldn't do it faster than that. So here you see the observations of the chirp clearly seen in Livingston and in Antwerp. We had a glitch in the Livingston data, so that was what took long to fix that, to get it out. And it was very unclear what was happening with Virgo, because the event was so close by and so high in signal over noise that it was surprising that we didn't see a big signal in Virgo. And it had to do that the signal and the antennas, the interferometers, have blind spots. And this event was close to a blind spot, which actually helped then to localize where the event was. So what we have seen is the collision of 2 neutron stars. So I show you a neutron star in comparison to Valencia, so it's a similar size. And it's kind of amazing that you can see the collision of these objects about 130 million light years away. You cannot see them with a telescope, it's impossible. But with gravitational waves, before anybody sees them, we can see them. We see them going around each other. We can determine the masses, the spins. We can already, from the analysis, maybe see some tidal information. We can see how much energy will be radiated in this collision. So there's lots that you can do with gravitational waves that you just cannot get at in any other way. And then it was seen, so this, the nice thing with now drawing in all the astronomers is that you also get nice videos. This one I think was made by NASA. So you see 2 neutron stars colliding, and then 2 jets going on, gamma rays, that were seen by Fermi and Integral. And then you get this oven where all the elements were created, and I think, I don't want to bore you with that, you might have seen this many, many times. So I will not do that. So here you see the signals, the time observable. We have to do the function of time for the black holes that we have seen. And now you see this binary neutron star. So if you look at that, you immediately see this is a different thing. These are 2 neutron stars. This goes on. In total, if you start in the order of 20 Hertz and higher, it takes about 100 seconds. So I'm not that patient, so I will continue. But it's clear that this was a different object. This was a binary neutron star. At least that's what we think. It's difficult. We know that one was a neutron star. The other we are still arguing. And also the final, the remnant, it's not really clear what it is. So with 3 detectors you can do triangulation. Actually, you get more information with gravitational wave detectors because they have antenna patterns too. So it's not only the time of arrival, but also the antenna patterns that we use. And then you get the sky localization, and this is the sky map, where then people have to look for counterparts. So it took us a while to produce that, and it was about 30 square degrees. 31, 28 square degrees after analysis. But that again takes another day. So seen by Integral and Fermi, actually here you see what you learn from that. So you have this, this is the signal that we have been seeing, then here is the merger, then you wait 1.7 seconds and you see the gamma rays. So by assuming that the gamma rays are created within 10 seconds from the gravitational waves, you can compare the speeds of gravitational waves to the speed of gamma rays. So that's one thing that is in the papers. But the other thing is that, of course, these electromagnetic waves and gravitational waves, they have to go through potential wells. So even if you look at the potential well of our Milky Way, then you would get Shapiro delays, so time delays and different trajectories that you have to take into account. So you can test the equivalence principle for gravitational waves and electromagnetic waves. And we did a test to 1 part in a million. If you take all the galaxies in that 40 megaparsec, and you look at the peculiar velocities of that, you can make another estimate of the gravitational potential, and then you do a test of the equivalence principle to 4 parts in a billion. So these are kind of things that we did. You can ask yourself, why did you do that? Why is this interesting? It's interesting for dark energy and dark matter because it has consequences. For example, if you now look at dark energy, then what you could try to do is make a theory of dark energy where you add scalar fields to your theory, and the scalar fields then have to generate in combination the effects of that you see in that dark energy. Now, if you do that, then there is a general tendency in many of these theories then to get an increased tensor speed compared to what you see electromagnetically, and this then so I give you the publication there, and you can look it up. This led to an exclusion of several theories that are not viable anymore, but still there are other ones that still are viable. And then the effect that you can go through this, also these potential wells. In general, you can make dark matter emulators, so you don't believe in dark matter in these theories, but instead you make scalar fields, and these scalar fields then should mimic the effects of dark matter that you observe. In general there, you get different geodesics, so different paths for photons and gravitons, and again you can put limits also on these dark matter emulator theories. So that was interesting. The other thing is that when it became known, and we did this through circulars, that there were gravitational waves observed coincident with these gamma rays, then astronomers got excited and they started looking. So this is another, I think, NASA movie where you see that the Hubble Space Telescope was pointed at this object. Actually, it was the SWOG collaboration who found it within a few hours, not the Hubble. But they made the nicest picture of the galaxy. So that is what you see here. So the galaxy was found in a matter of hours. And you also see that this is the collision of these two neutron stars outside. That has to do when you form these systems that they go supernova, they get kicks, and they are ejected outside the center of the galaxy. The other thing, and then all the instruments worldwide, I think every astronomer that had access to a telescope that could walk, I think, did observations. This event here is here you see the gamma ray bursts that are typically observed. You see it was the gamma ray burst which was closest by, but also the weakest by far. If this same object would have been here, then the dashed curve here is the sensitivity curve of Fermi. We would not have seen it even with Fermi. This is a special event. I don't know how many of these we still are going to see. And here you see, if you would have had only LIGO, it could have been on this circle indicated by green. With Virgo, we are. This is a sky map that we released after 5 hours. We intend to do this on a time scale of minutes now, maybe 1-2 minutes in the next run. Then this is from the timing of the two satellites, and this is again a detector within Fermi. So this is the overlap region here with the gamma observatories, and then in here. There are about 50 galaxies, billions of stars, and here you see the observation, I think, with SWOG and also with radio of where the BNS was observed. So the other thing is that if you look at this, you also see that it's a rapidly decaying transient. So in a matter of a few days, you go down enormously in emission, electromagnetic emission. So it will repeat. And if you look at the color of the source, then it goes from blue to red. And the other problem with this source was that it was close to the sun. So when So it was observed, say, by observatories in Australia, South Africa, in Chile, etc., every 6 hours. But it was rapidly decaying, and there was only a window of about 1 hour to do the observations. And at some point you couldn't observe it anymore. We were too slow, I think, with releasing, because right now it is still not clear what the mechanism is that is covering this supernova, whether it's a shock and whether you expect some exponential decay, or whether in this radioactive cloud, when you generate all these elements, it is building up in time and then decaying. The bottom line is that everything that you see here in this yellow are the elements that we believe are created in this event. Am I running over time right now? I am? Okay, good. So some more things about the physics that you learn with these events. So this now is involving neutron stars. So neutron stars are extremely rich physics laboratories where many aspects are coming in. I just listed a few, like proton superconductivity, neutron superfluidity, where the magnetic fields coming from. And the whole idea is to try to determine the equation of state. I will have to disappoint you a little bit there, because lots of the information is actually coming in the gravitational wave signals at high frequency. And at high frequency, right now, our detectors are not sensitive enough. And they are very sensitive between, let's say, 100, 200, 300 hertz. But if you start talking about 2-3 kilohertz, where there is lots of information, we still have to improve our sensitivity. So we will do that. We can say a little bit right now that if you look at this equation of state, it's essentially saying that if you have a certain mass of a neutron star, so how compact is it? And we favor maybe a soft equation of state, a more compact radius, more closer to 10 than to 15 kilometers. But this is certainly something that we will continue to study. So we need to get better on these high frequencies. Another way to get information is through the tidal interactions. So if these are deformable objects, then tidally they will deform each other. And this gets imprinted on the gravitational waves that are emitted. So we also use that to gather this information. And one of the things that in Virgo we are leading in is on these kind of calculations, so numerical relativity combined with matter. For some reason, this is dominantly pursued in Europe compared to, for example, what LIGO is doing with black holes in the US. So excellent work here. On this equation of state with this one event will be difficult to say something, but as soon as we get maybe 30 or 50 of these events, then we should be able, by combining the information of events, to start picking out equations of state. So I started my career as a nuclear scientist, and I did nuclear physics experiments. Then I went into particle physics and now gravitational waves. And already 30 years ago it was a big topic. What is the equation of state of neutron stars? I never expected that I would learn something about it by colliding neutron stars together. Anyway, but it's good, I don't complain. Another thing that you can do with these neutron stars is that I told you that from the gravitational wave signal you can get the distance. So you have a different way to get at the distance, and as soon as you then also have the redshift that you can get from electromagnetic observations, you can start doing cosmology. The advantage of gravitational waves, or a property, is that you get the distance in a different way than you would do it with supernova 1A. So we try to do this. This was already, I think, known in the 80s that you could do that. So we try to put this in practice with our event. And so we measure the Hubble constant, so the local one. And it's the probability is given by this blue curve over here, and we compare to the purple and the orange, which are the values from CMB and supernova 1A. Of course, we have a very big error bar. It's plus or minus 12% compared to the few percent error bars on the other experiments, but we just have started and got one event. But you also see that the existing measurements right now have a discrepancy of the order, I think it's 9% right now, the most recent value. I think that is like 2 weeks ago. So there is some tension there. And again, by measuring a set of events, maybe again 50, which I think is really realistic for LIGO Virgo to do in the next several years. Because every time that we improve with a factor of 2, our event rate goes up by a factor of 8. So, and we still see many possibilities to improve. And then we should get to this Hubble parameter to a precision in the order of 1–2%. So this is another thing that I think will happen reasonably soon. Now with third generation observatories that we intend to build in the future, we can even go much further than that. We can look at the physics state parameter for dark energy, look at the Z-dependence of that. So there are many more possibilities with gravitational waves. So this is just the first thing that we are doing. So what you see, what is happening right now is that a broader and broader community is now starting to use our results and relying on detection of gravitational waves. So that means that the pressure on us in the observation mode is increasing and increasing. So I showed you some examples from fundamental physics, and there are many, many more possibilities, even things like parity violation. If you start coupling your Lagrangian, in there you can look at parity violations for gravitational waves if you want to do that. So this goes on. Astrophysics, I told you a bit about that. Of course, there is the whole astronomy to get at the populations, about the distributions of these objects as function of redshift, the mass distribution, spin distributions, etc. We were all starting to collect that, and but I didn't talk about it. Yeah, a first glimpse now on cosmology, and you also see that we are affecting that discussion right now, and nuclear physics. So, so hopefully we come back at the second half this year. We are thinking about October, November to be online, and then we should have a factor of 2 in sensitivity for the network improvement compared to what we did. That is the ambition. That's what we're working on. If we can realize that, I don't know. I don't know yet. We are still working on this. So a few words about the future. So this is what is happening with these Earth-based experiments. And there is more, of course. There is a detector under construction in Japan. And it's 1 kilometer underground in the same mountain, the Kamioka mine, where you also have Super Kamiokanda. It's being built right now. They already had lock of their interferometer, so it's installed. And there are discussions with Kajita going on to see if they even could join at the end of the next observation run. Then there is an approved project for a third LIGO interferometer in India, and that hopefully could be online in 2024. So also there are developments. But there are other developments like LISA. This is a project right now of the European Space Agency, and this is approved. This is a large mission. It's actually a launch date in 2034. So this becomes challenging for me. So I'm considering to go on fitness and things like that because I want to see this happen. LISA launched the Pathfinder mission. And this was in December 3rd, where they have these 2 cubes, which are the LISA test masses, for 38 centimeters apart, and then measuring with a reference laser and a distance to get the distances between these test masses. And so this was a tremendous success. So they already announced in 2016 the first results in blue, and now recently this was published, and you see that over that whole frequency range. So LISA is an interferometer in space with arms millions of kilometers apart, and that means that you can measure at much lower frequencies. So you start measuring around millihertz frequencies, so much larger objects. And but the performance for measuring these small distances was already achieved with this Pathfinder mission. Very, very exciting. And this is an approved experiment that will happen and will be fully complementary with what we want to do ground-based. This technology will anyway be flying soon again in the GRACE follow-on mission. These are these two satellites that are dropping in the Earth's gravitational potential. So one is dropping, and by a link you measure that with the other one. And this technology will also be used in the follow-on mission. And with that you can measure the gravitational map of Earth. And for example, if you look here at the gravitational field over Greenland, you see that it's decreasing over here because the ice coverage is decreasing. You measure the total mass, the total gravitational field, not the height. So if you have any doubts that the climate is changing, and look at these data. This will become much more precise with LISA technology. You can see over large areas millimeter changes of water levels. And water in our planet will also become quite important. In the future, they have been thinking about looking at magma rising in chambers of volcanoes. Then with Virgo, we intend to, we have a design sensitivity of something like 130 megaparsec. So imagine we are at 26 right now, and we are talking about 130 to make it in the design. But there is a new project defined that's called Advanced Virgo Plus, where we want to double. We want to go to 250, so tenfold compared to what we do right now. In the event rate, it is a factor of 1,000. That's what we try to achieve. So that project is called Advanced Virgo Plus. Of course, we need to find resources to do that, and groups that want to help in realizing this. And so essentially, our science is limited by event rate. So it's very simple to defend the science case. We just need more events. And we are only looking at the very local universe. So we want to implement new innovative technologies. For example, we are limited by quantum effects. And we want to inject a squeeze light to overcome that, and other things. So here, by doing all of these improvements, we should end up somewhere by a factor of 2 better sensitivity. So our core expertise is actually in Virgo, is on the mirrors and on the coatings. So we have mirrors right now 35 centimeters diameter, 20 centimeters thick, 40 kilograms. We do then polishing to an incredible level, fraction of a nanometer. If you would take a mirror of Virgo and you would magnify it to the size of Valencia, then the flatness of that mirror will be the flatness of a human hair. So it's absolutely brilliant how these, it's the closest you can get to an ideal optical mirror as you find them in the textbook. And what we want to do now is improve that, make bigger mirrors. So not 40 kilograms, but more than 100 kilograms. So that means you have to do everything robotically to do the coatings, and then you have to stack the coatings. So all these layers up to microns, but still be sub-nanometer precision on large surfaces. That is what we are doing. And also, what you might not know is that these mirrors, the coating of the mirrors, also of the LIGO mirrors, the mirrors in Japan, were all done by Virgo. They were done by LMA, a group in Lyon that is doing this coating. So we heavily invested in that. And that is also what we want to do in future. So we want to scale this up. So we have more impressions. So LIGO is doing the same. Their improvement is called A+. And both of us are synchronizing everything that we do. It's like one consortium. So our data sets, for example, our data format is exactly the same. We completely agree when we are going to run. There is no Virgo data analysis group or a LIGO data analysis group. All the data analysis groups are completely merged together because we believe that our science just improves from collaborating. And also we try to run together, and we try to be ready with this upgrade before 2024. So let's see if we can manage to do that. And that is the best I think you can do with LIGO and Virgo, and then that is the limit. So of course you know that in astronomy what you want to do is you want to look back to the early universe, so in terms of redshift, so the factor with which the universe was smaller compared to now. And if you have seen these beautiful pictures of Hubble, then with all these galaxies, then you have to think about a redshift of maybe 10, 12. And that was the best that was done. And maybe with James Webb we can go to a redshift of 20. Now, if you look at the events that we are seeing right now, we're talking about a redshift of 0.2. So the events that we are looking at, I then say, these gravitational waves have been traveling for billions of years, but it's very local. The universe is really incredibly big. So what we want to do is not measure this local universe, and even with the upgrades in LIGO and Virgo, we will not go further than here. That is what we can do. So if you want to look at these kind of collisions in the entire universe, you need a new instrument. And that new instrument is for Europe Einstein telescope. So we already did a conceptual design study that was funded in FP7. It is on the roadmap of APEC to realize this somewhere in Europe. And there are different places that have an interest to realize that. The news was Italy with Sardinia last week, very big in the news that they are offering the possibility to host this in Sardinia. The background here is somewhere else. And then, so if you would have an instrument like that, I think you would see until the Dark Ages, so you would see before the formation of the first stars. So if you then see black hole formation collisions, you know that they're not stellar objects, but maybe primordial. You can look to very low frequencies. You want to look to very low frequencies because all these spin and spin orbit effects, they give all kind of precession effects. And you need long observations in order to see that. We think that we would see something like 100,000 of these events, of these collisions per year. So it's a lot and overlapping. And I think it's a nightmare if you start thinking about how to do the data analysis, how to make the waveforms to do that. I think all of these issues are not solved at the moment. The other thing is that we are in a network right now with astronomers. We have 95 agreements with groups in astronomy to give alerts, and then they can point the telescopes. We are now going to give open alerts. So everybody just can follow up and look at that. But with Einstein telescope, more than a day in advance, you can tell where the sources will be, because you already get enough signal over noise. You also, if you are fast enough in your analysis, you can even pick out the interesting events. I don't think you want to point Hubble every day to a source like this, but only to the interesting ones. So this is a huge computing problem to do that. Then on testing the theory, we can do this at the super mil level. We have so many events that we can combine. The events that we had right now, well, you would see them as signal over noise ratios of close to 1,000. So very, very precise. I think our numerical calculations right now are not even at that level of precision. And then I think the other thing is that maybe 15, 20 years from now, there will be several big data sets from SPA, LSST, maybe TCS. And I think if you would also could combine that with huge data sets in gravitational waves and correlate all of that information, I think that would be the new way to do astronomy. So I think with a device like that, we can look at what is happening close to black holes. Black holes are interesting. In theory, they contain a singularity. The only other system is the Big Bang itself. We can test, we can do cosmology with that device, and maybe we have a chance to see something that is primordial, but that is difficult to predict. Depends how the theories are. So I think there is a very bright future for our field, not only Earth-based, but also space-based with LISA. And there's more, lots of timing arrays, cosmic microwave background, looking for gravitational waves. Third generation, and I think now is trying to optimize the science that we are getting out of these events. I think that is important, and getting these projects on roadmaps. Thank you.
Thank you. Thanks for this very complete and exciting overview. We have time for a few questions.
was a very nice talk. I mean, the fact that you said you were surprised seeing black holes before neutron stars. And the question is, are there more black holes than we think? Less neutron stars than we think? Or is it just a question of the signal to background ratio?
No, that's what we did before we started measuring. Already in 2012 and 2013, we released a paper about the rates estimates for the different events. And then, based on what we know from astronomy and population models that we made predictions, for example, for binary neutron stars and for binary black holes. The binary neutron stars, the prediction was that if we would achieve design luminosity, the design, see, I'm particle physicist, design sensitivity, then, sorry, design sensitivity, then we would expect 40 BNS events per year. But the uncertainty on that number is about 3 orders of magnitude at least. So 1 a year. So because the thing is that we didn't have design sensitivity. We had about a factor 3 to 4 less. So that means that you expect maybe 1, 2 a year or 1, 2 per 1,000 years. So that was difficult. So you had to be lucky. Now the predictions for binary black holes were even more off. Then the predictions for black holes in this mass range, they were not the ones that were observed from looking at the X-ray binaries. This is where you look at the gas going around an object and then try to, from the Doppler shifts, trying to infer the mass. Then you would think that you have seen black holes maybe in that way with up to maybe 15 solar masses. So it was quite a surprise to see these kind of events.
So to say, I mean, from that we cannot deduce, I mean, the rate of formation of black holes or neutron stars. Not easy.
No, I think the predictions were very limited. So the good thing is then that if you then can detect them and you can do gravitational wave science, then indeed you're bringing new knowledge. You're really now learning about how are these populations and what are the rates. But they were very, very uncertain. There were some people that predicted heavier systems, but even right now it's debated how did they form. And so are they stellar mass objects or are they primordial? Or there are many proposals for formation of these systems.
Further questions?
On the question of possible quantum gravity effects in this system of 2 black holes with these catastrophic events, you see, this system reminds to me, more than 100 years ago, there was the problem of the classical Rutherford atom. The classical Rutherford atom would be like that, okay? With the motion of the 2 particles once the nucleus had been discovered, the nucleus of the atom. And when I heard the news about the origin of the gravitational waves that you detected, then immediately I thought, okay, what is the Bohr radius for this system? Because this is the only thing that could stop this, to see quantum gravity effects. And in a back of envelope calculation, I discovered that the Bohr radius is smaller than the horizon in these black holes, which would prevent, in my opinion, to see quantum gravity effects. This is the reason why I asked you before the colloquium about these possibilities. I would like to know your opinion about it. You see, ideas or whatever to look precisely in a system as this one, which is probably the most catastrophic event that you can imagine in the universe, whether quantum gravity effects could be observed.
Yeah, so I think the answer is, the honest answer is that we don't know. So it could be that indeed, if you look at the effects of quantum gravity, if they are there, that they would always be behind the horizon and you just could not probe them. That is a possibility. I don't know. The other theories that are on the market, for example, if you think about firewalls or other effects, then, for example, gravastars, then people are talking about the echoes that might reveal structures at Planck scale distances, because through general relativity effects that get stretched to milliseconds in echoes that we in principle could observe. We didn't see anything yet. So that will be a possibility. There are the stories with gravastar and firewalls that the matter is not going over the horizon because that information is part of the story. If that would be true, and you would have collisions of these objects, wouldn't you then expect electromagnetic counterparts when you collide black holes? And people are looking for that, and so far we have no evidence for this. But if we would get evidence that with certain black hole collisions we would see electromagnetic counterparts, that would immediately go against general relativity. What we also can do is we can measure the spin of these objects, and you know that in the natural units the spin has to be less than 1. So now imagine that we would observe something and experimentally and the spin would be larger. Then you would think about naked singularities and stuff like that. So I think what I'm hoping for is to find something that deviates. But that is up to nature. I cannot control that. So, but I think there are certainly possibilities. But it could also be that you're right, that if it's there, it's behind the horizon, you never learn anything. That would be disappointing for me. But at least now we can measure. And now many of these alternative theories have to take serious the fact that now there is a group measuring this.
One last question. If there is no one else, I'll ask mine. So you mentioned dark matter and dark energy, and of course these are big issues also for particle physicists working on colliders and direct detection experiments, etc. And you've shown that some maybe a bit more baroque models can already be ruled out by the current data. But how rigorous can all this become? Can we really start to distinguish between WIMP, dark matter, and axions and modified gravity explanations, etc.?
Yeah, in principle you should be able to do that, but the problem with it is that if you see the level of quality to what general relativity has been developed, and that how we can use it in our analysis and our understanding, then many of the alternative, what you call theories, are not at the level that I would call a significant theory. And so I could imagine that, for example, you would have these alternative models where you would have dark energy, which then maybe have to do with structure of space-time, that they would affect the phasing of gravitational waves. But then it would be good that the people that are making these models come to a level of prediction that we can test. Because right now, I think, I don't know that these theories are at that level.
Mm-hmm. The data can be made precise enough in principle, you think?
Yeah, if you look at our results, so I think if you project that into the future of third generation, then everything that you will see there, you will have about a factor of 30 better precision on all the curves and all the data that we measure. And instead of a few events, you will have, over a period of 10 years, you will have 1 million of events. So there is a tremendous amount of science that you can do. But then are your alternative theories at the level of maybe making these predictions, and are they varying from GR at the level of a percent or not? Right now, I just don't know that. I know, of course, that many of the statements that I hear, but it's very qualitative. And this is precision science.
Okay. Andrea, one last question, and I missed it.
this is just a quantitative question. Once the Japanese detector and maybe the Indian one will come into operation, how much you can reduce the localization capability of the event?
To a few degrees, square degrees. So roughly what you see is you see the width of these rings that we are projecting. And then if you get a couple of them that are crossing, it is that cross-section that decreases it. So it will be a few square degrees, not better than that. And this already depends on what location the source is. If it is a bad location, then it will be worse. But you see that already with Virgo, with the very limited sensitivity that we had, we went from the typical 1,000 square degrees to 28 square degrees. So there are, I think, possible improvements there.
Okay, let's stop here and thank the speaker again.